Okay, so this is the second part of our amplifiers lecture. Last time, like I said, we looked at the characteristics of ideal op-amps, and we looked at the use of an ideal op-amp in our first amplifier circuit, which is the inverting type amp. Just to recap, amplifiers, they're useful in instrumentation measurement systems to amplify low-level signals. We have quite a number of sensors that will give out low-level signals, like thermocouples, strain gauges, RTDs, which are resistance temperature detectors. Some of those give out their signals via a Wheatstone bridge, right? And the Wheatstone bridge output voltage might be quite low because the change in resistance in a lot of cases is low, right? And you make sure you keep it low, because by keeping the change in resistance low, you keep your output linear. If the change in resistance is too big on a Wheatstone bridge, you're going to end up with a non-linear type response. So we need to use amplifiers for that. We looked at looking at ideal op-amps and applications. We looked at the practical or limitations of practical op-amps. And then at the end of, towards the second half of the lecture today, we'll look at instrumentation amplifiers. There are 5 basic voltage amplifier circuits. And the inverting amp, we already started looking at. We're going to be looking at the non-inverting amp, which is good because you don't get a negative voltage out. You get a voltage of the same polarity as the input. We'll look at the voltage follower. We'll also look at the differential amplifier and then the AC amplifier. So these are 5 different voltage circuits. And after we've looked at those, we'll look at the special case of what we call the instrumentation amplifier, which is the most kind of common one, if you like. So like I said, this one, the inverting amp, we started on last week. And just to recap, this is it. If you recall from last week, what we have here is our op-amp, which we assume is ideal, and some characteristics of the op-amp that we'd have spoken about, and the fact that it basically assumes you have infinite impedance across the poles on the input side. So there's a kind of link between the negative pole and the positive pole. So the impedance between the two is infinite. That means you can't get any current flow. So you always have kind of a stagnation of current at your poles, which is why here we have this current here as equal to 0, right? But what that also means is that you have equal voltages on both your poles, or let's say opposite voltages. So the voltage at your negative pole is the opposite of the voltage of your positive pole. You also assume there's infinite gain across the op-amp itself. Those are some of the characteristics. We also assume for an ideal op-amp that we have what's called infinite common mode rejection ratio. That means that the common mode, whatever equal voltage applies to both the poles, that should all be rejected. So in other words, the amplifier really only amplifies the difference in voltage between the two. So with those conditions in place, we can start to construct the governing equations for this little op-amp circuit. And we know for a start that we have no current flow here. And that means that if we have a voltage drop across like a positive voltage on the input side, here, which is connected to a sensor, and some input resistance, then there'll be a voltage drop, which means there has to be some current flow, right? Because V equals IR. You've got an I equals V upon R, so therefore if you have a positive voltage and a positive resistance, you have some current flow. But current here is 0. That means your current flowing in this resistor has to actually be matched and cancelled out by the current flowing in this feedback resistor, R2. Right, so that means that I1 equals minus R2, basically. They're equal in magnitude, those two currents. So that's our first condition. And we also know that the current in the R1 is V upon R, V in upon R1. Current in R2 is V upon R, V out upon R2. Right, and those added together will come to 0. So in other words, one is the negative of the other, same magnitude. So if we substitute in our expression for I1 and I2 into this equation, which is derived, like I said, from the characteristics of an ideal op-amp, then we can resolve this to get our output voltage, which is what we want to find, right? Or we might be interested in what's the overall gain of the amplifier, output over input. Right, so if we're looking to express it in terms of the output, then the output is given by, well, we have to take this term, Vn upon R1 across to the right-hand side, that makes it a negative, and then multiply out by R2 to give us our V out, our output voltage. So that's why it's called an inverting amp, because our output voltage is negative of our input voltage times the ratio between R2 and R1. So R2 is the feedback amp, R1 feedback resistance, R1 is the input resistance. So the ratio or the gain of the op-amp, although the ideal op-amp has infinite gain, the practical gain of this amplification circuit is actually negative of the ratio of R2, our feedback resistor, to R1, our input resistor. And I think last time we said as well that for an actual op-amp, what we need to do is make these pretty large, these resistances wide. Why would you make them big? Any ideas? What would be the benefit of, like, let's say you could have, if you want to do a 2-to-1, like a 2-to-1 amplifier, you could either do 2 ohms and 1 ohm, or you could do 200 kilo ohms and 100 kilo ohms. What's the relative benefit of doing, you get the same amplification, what's the benefit of doing 200 kilo ohms and 100 kilo ohm rather than 2 and 1 ohms? What's it going to affect? It's not going to affect the voltage. You get the same input voltage. But if you have an input voltage of, let's say, what might you have? Let's say 1 volt for simplicity, right? If you get 1 volt in and 1 ohm, your current is 1 amp. And power dissipation is going to be what? P equals I squared R. It's going to be 1 watt. 1 watt. 1 watt. Right? And on the other side, you know, you're going to get a commensurate power dissipation of this is going to be 4 watts, right? Because you're going to get 2 amps in this. No, beg your pardon. It's going to be 0.25 of a watt. Because your currents will be, if this is twice the resistance, your current will be half. Half squared is a quarter, so it's a quarter. It's a quarter of a watt, but still, that kind of level of power output on a resistor is actually going to cause some significant heating. That's going to create increase in actual resistance of those devices, and you start to skew the output of your amplifier. And because the heating or the power dissipation in the 2 resistors is different, then you're going to get a varied effect, and therefore the actual ratio or the amplification that you get is going to change as the thing gets hotter. Right? So I say all that to say, well, for that reason, you don't put 2 ohms and 1 ohm. That's why you put 200 kilo ohms and 100 kilo ohms. Right? Just indicative. To get the same amplification, because with 100 kilo ohms, then you get a very small fraction of 1 watt. 1 times 10 to the minus 6, right? Amps flowing through, which gives us 1 microwatt of heat dissipation, of power dissipation in the amp. Right, so you can see why you want to keep your resistances high. Normally, R2 is actually much larger than R1 because you generally want a gain of more than 2. I was using 2 as a simple example, but you might want a gain of 100, 1,000. something of that order of magnitude, that means you need to have a much bigger R2, feedback resistor, than input resistor. And so R1 is not large generally. Output impedance is ideally 0, but generally low. That's the output from the op-amp itself. And that means that you can actually use so the outputs, on the output side, you can get a decent current flow, right? And that's also something you might want in your circuit, especially if you have to use that output current to drive something, right? Whether that might be an analog to digital conversion or a gauge, some output. So you do generally want some low output impedance. So you want high input impedance. That means that you get minimal current flow on the sensor side, but on the output side, you want low output impedance so that you can actually generate current flow if you want it on that side. And we noted this, the maximum current flow that an op-amp can handle is very small, about 20 milliamps. I forgot to start recording, so I might just cancel this one. Oh no, I am recording. Okay, good. I have to cut that bit out. All right, the inverting amp, therefore, we can do something with it which is quite clever, which is use it as a summing amplifier. So we could actually add two voltages together and amplify them, or rather average those two voltages. So if we have an input, let's say two inputs, V1 and V2, we can use this inverting amp. This is an inverting amp because the positive pole is connected to ground. Right? That's a clue for an inverting amp. But what we have here, like I said, is two inputs. We've got R1 is our V1 input. R2 is our feedback resistor. But then we also have this R3, which is on our second input. And if we work that through, basically, you do average out the output voltage is really the average of the V1 and V2 times the relative gains of each path. So the gain of this path to V1 is going to be V1 times minus R2 upon R1. The gain of the V2 path is going to be minus R2 upon R3. Right, so you basically just get the average of these two. So if R1 equals R2 equals R3, then in other words, all of them are the same, and you don't get any gain, but it just adds up the voltages, right? So that means you can use it then as what we call a summing amp, where it just purely adds up V1 plus V2. So it's a little op-amp application, a circuit you can build with an op-amp that allows you to do something that could be useful in your measurement system. Alternatively, if R1 equals R3, if we have the same input resistances on the two input sides, and R2 is half of those, right? So then that's how you get the average of V1 and V2. So you can do different things to manipulate your input voltages, get different kinds of outputs. So here's an example where we want to actually get an output that is given by this equation. So a bit later down in the lecture, we'll give you an example where you have to decide what the equation needs to be to give a certain kind of output relationship. But for now, I'll give you the equation. The equation is that you want your output voltage to be 3.4 times your input voltage plus 5. So if your input voltage is 0, you want to give a 5 volts output. If your input voltage is 1, you want to give 8.4, etc. Right, so that's the relationship we want to establish, and we need to build or design a little amplifier circuit to do this. And in the last slide, we got the information we need to do it, because we learned that you can use an op-amp as a summing device, right? If you put it in the right kind of circuit. So there are different ways you can solve this problem. But one way is to use the summing amp, but now we've got basically two inputs. One is V in, or V here, and then the other input is a constant of 5. So you can see that this basically corresponds back to the last slide, which is here. So you've got one relationship between, if we take V1 as our input, so in this case, you want to gain here R2 upon R1 of 3.4. And this V2, we can make this a constant 5 volts. But we want a unity gain, right? R2 upon R3 has to be 1, right? Now, the only thing is you do have to deal with the negative aspect of it if we're going to use this. So our gains will be 3.4 for this pass, so the input resistor will be 1 upon 3.4 of the feedback resistor. And this one is going to have a gain of 1. However, this will give a negative output, which we then have to correct. We have to correct that. And there's a way we can do that. We can basically just use another op-amp or another inverter amp, but with a gain of what? A gain of 1, right? So you just flip it. So we can use a unit gain op-amp, inverting op-amp to correct this inversion and get it back to what we want it to be and get this equation. So if we put this into a little diagram now, this is how it would look. Well, the 5 volts is on the upper branch, let's say, and we want the relationship, our feedback resistance over our input resistance to be 1. So, but on the input branch, the V in here, we want our ratio, our amplification, or our gain to be 3.4. So you have to have 3.4 times the feedback compared to the input, right? So that's what we have here. Note that 34 kilo ohms, right? We're putting the resistances up in the kilo range to keep that current low. So if we use 34 kilo ohms and 10 kilo ohms, that gives us a 3.4 ratio on the input voltage. On the constant 5 volts, we can use 34. Well, we already have 34 for the feedback. We can match that on the input resistor and have 34 there as well. And we've got our gain of 1. All right, so at this point, we have our output is negative 3.4 times our input plus 5. But we now need to correct that by flipping it. So now we have 2 matched resistors on this next inverting amp. It's inverting because positive pole is connected to ground, right? So you look for that, you recognize, okay, this is an inverting amp, and I know which equation I have to use, one with the negative at the beginning. Right, but now this negative voltage output flipped, so I have positive voltage output on this side. So we're building up simple circuits using the op-amp as the kind of core component, but then we're building these circuits around it using varying resistances to give not only a gain, but now in this instance, we're actually able to create a voltage relationship between the input voltage that we have from our sensor and the output voltage that we want. So if I say you have a thermocouple and it gives an output voltage of 3 millivolts to 7 millivolts, but I need to get an output voltage from my amplifier of 0 volts to 5 volts, you should now be able to figure out how to convert it, right? You should be able to figure it out. You're going to need 2 things. You're going to need a gain on your signal to give you the right relationship between the range of values of the sensor, which is 3 to 7 millivolts, to 0 to 5. So you need that gain, but you also need an offset because you have to correct for the fact that 0 is 3. So you need a negative voltage to pull down That's where this constant value offset will come in. So you can actually do it with a circuit just like this. You just have to change the values to get it into something that could work. Let's look now at a non-inverting amp. So we looked at the inverting amp. The non-inverting amp is a little more complex in its configuration, but it does have a big advantage in as much as it is non-inverting, right? It doesn't flip the output voltage. So now, if we look at the diagram of it here, we see the input voltage goes to which pole? Positive pole. And the negative pole is connected to ground, but through a resistor now, right? And we still have the same sort of setup with a feedback resistor going to the output. So different kind of setup here. Feedback resistor connected back to the negative pole and through this resistor directly to ground. So, do you want to try deriving the equations for this? No? You want to try it? You start with some very simple rules, right? The simple rules are that you stagnate your current here because no current can flow through this op amp. So you have to have a kind of a mean current here of 0. And then we also know that the voltage at the positive pole is going to be negative the voltage at the negative pole. So if you start from those two simple rules or characteristics of the ideal op amp, you can actually get to derive the output. So you want to try? No? All right. All right, so we have to determine the voltage at point S here. What rule are we going to use to determine that voltage? Well, if we look at the circuit from here, you've got an output voltage, and it passes through one resistor to the voltage we're interested in, then it passes through another resistor to ground. So what rule are we going to use to determine the voltage at this point here? Potential divider rule, right? So if we want to create an expression, we can say that V at this point called S on the diagram is going to be R2 over R1 plus R2 times V out. Okay. What else are we going to get? This is the final, that's what we're trying to derive, what we're trying to prove at the bottom here. What else can we say? Well, based on the relationship here across these two poles, we know that the input voltage is going to basically force this voltage at the negative pole to match it. Right? That's also another relationship with the op amp. V negative equals V positive, right? Remember that rule? And the other one, by the way, is I at negative equals 0. There's no current flowing through. So, in which case, what we're saying is that we basically substitute in for this Vs. This is actually going to become our V in. And so it becomes a very, very simple solution actually. We also know that I1 in this resistor R1 is going to be equal to minus I2, or you could say I1 plus I2 equals to 0 because the stagnation thing. If you want to find I1, that's going to be V in over R1. I2 is going to be V out over R2. Sorry, no, it's going to be V out minus V in, right? This is going to be the same. V out. So from those relationships, what we now want to, I want you to get V out equals what the relationship. We should come out looking like this. Okay, so our non-inverting op amp also formed from the same op amp, and you know, we went through the logic of this because you have zero current flow going through our op amp, then V at negative has to equal V at positive, so V at negative equals V in. Using the potential divider rule, getting it the right way around, with R1 on the top and R1 plus R2 on the bottom to make sure we get the drop-offs in voltage correct. Then we get our V at negative is going to be V out times R1 over the total on that path, which is R1 plus R2. And now, of course, our V plus equals V minus, so that's V in, and we can get it in this form. So that's our non-inverting amp equation there. So here's a little example. Develop a high impedance amplifier with a voltage gain of 42. So that's what we want to get. The key being high impedance. Right, so we want to minimize current flow. That means that upstream we want to have a significantly large sort of resistance. So we can use our non-inverting amp, and we could use a nice big resistor for R2, say 40, let's say 420 kilo ohms, and then we would use what, 10 kilo ohms on the bottom, and that gives us a ratio of 42 here. Except it doesn't need to be 42 because you've got a plus 1, so it'd be 41, right? So you've got 41, and that would do it. But well, and we give kilo ohm resistors to make sure it's high impedance. So our next type, that's basically non-inverting amp then. Our next type we're going to look at is the voltage follower. This one is a very simple device that basically just gives the same output voltage as input voltage. Doesn't amplify anything, doesn't give you any gain, or has a gain of 1. So why? What's the point of having a device like this? Any ideas why you might put this in the circuit? It would generally be combined with other types of amps, you know, as well. Well, what qualities does this give you? Well, what it can do is it allows you to kind of separate out your sensor from your amplifier circuit, right? And the quality of, or the characteristic of your op amp on the input side is, what do we say it has on this side between these two poles? Very high impedance, right? So we basically put a device in the circuit with the sensor on this end that's very high impedance input. And on the output, the property of the input of the op amp is very low impedance. So that then allows us to have a better, a higher level of current flow on the upside. We haven't got any gain of the same value of voltage out as you get in, but the quality, you're now using the characteristics of the op amp to help you manipulate and use your, develop an effective measurement system. So that one's really easy. So this is to isolate or buffer circuit elements from each other. And it converts high impedance voltage to the same voltage at low impedance on the output. So you can connect, for instance, a voltage source with high impedance to a low impedance load. A voltage source in this case would be the sensor, for instance. Low impedance load means you want to actually generate that power dissipation, whether that's in a coil to drive a kind of a gauge like a dial or something. Or if you're using this output voltage and you're controlling, you want to control an actuator, right? Something that's going to drive a valve or drive a motor, a stepper motor. Right, for those kind of situations, this might be part of a feedback circuit where you're controlling, you're taking the outputs from a sensor and then you're feeding that through to some actuating type device. So what we're doing here is connecting a low voltage source with a high impedance load, and the input impedance very, very high in the order of 10 megohms for a typical op amp. This one, I guess, a bit more interesting now. A lot of the time, we want to amplify not just kind of one input versus ground, but we're interested in the difference between two voltages and amplifying that difference. So a particular case in this situation is if we look at a Wheatstone bridge, we might want to amplify the difference between the two sides of the bridges, and that's a differential voltage. So a differential amplifier used for differential voltages, like Wheatstone bridges, thermocouple outputs, two common applications. An ideal differential amplifier will provide you an output voltage that's the gain times whatever the difference in voltage is. So now, instead of having just one voltage in, you've now got the difference and you're multiplying that by some gain. And this is how it's configured, the diff amp. This time, your positive pole is connected to ground through a resistor R2, which is matched actually to the feedback resistor. And then the two input resistances, the input resistance on each of your input side input voltages, that will be matched as well as R1. Now, if we track through here, we can use the potential divider rule at this point, and to get this voltage V+, the V+ is going to be R2 over R1 plus R2. Right, so we're looking at getting the voltage here, and remember, whatever the voltage is here, you're going to be driving this voltage to match it. And so that's again, the property of the op amp that we're using here. We're going to use, again, the stagnation of our currents, and we're going to use the driving of one pole voltage to match the other. So our stagnation currents tell us that the sum at the negative pole is going to be 0. Right, so if we can get an equation for I1, an equation for I2, we can drop those in. We are not interested in the currents per se, we're just using that as a property, so we're going to substitute out for the currents. So our current I1 is going to be what? Well, it's the voltage drop across here, V over R divided by the resistance R1. The voltage drop across here is going to be the difference between V1 and V negative. Right, we'll leave it as V negative for now. And then our voltage, our current I2, we're substituting in here, and now we're substituting I2. I2 is going to be output voltage multiplied by using the potential divider rule. It's going to be V upon R. So V in this case is the difference between our output voltage and V negative, right? That's the drop, the voltage drop across this resistor divided by the resistor R2. So the voltage drop is V out minus V negative over R2. And that's going to come to 0 because I1 plus I2 equals 0. And so we can actually rearrange that to give us out an expression for V minus. And you notice here, we already derived an expression for V plus, just using the potential divider rule quite simply on this branch here. Now we've also got an expression for the voltage V minus, and we know the two are equal, so we can put this equation to equate to this one and resolve it. That eliminates, I think by doing that, we can get an expression for V out in terms of V1 and V2. Right, now this V minus expression, since V minus equals V plus, we're putting those two expressions together and multiplying it out. So why don't you do that? Quickly multiply out this equation. Very, very light work, but I'll let you try that to get an expression for V out. See if you can come up with it. Okay, so this is the equation shown on the slide. You rearrange those. You get V out equals the gain R2 upon R1 times V2 minus V1. So a good example of an application of a diff amp is amplification of a load cell. Now, a load cell, if you recall from our strain gauges lecture, a load cell is when you put strain gauges around basically a block of say, for instance, steel, and you're applying a load to that load cell, which might just be as simple as a steel block. And as you apply the load, that thing's going to compress. It's going to distort, and it's going to create strain on its surfaces. So you apply strain gauges, two that are basically in line with the direction of the load that will actually compress, and the resistance will reduce, and two that are perpendicular to the orientation of the load, and those will, by Poisson's law, they'll actually be in strain, positive strain. Therefore, the strain gauge resistance is actually going to go up. So you configure those so that we kind of maximize the difference. So on each branch of a Wheatstone bridge, for a load cell, you have one compressive and one tensile strain gauge. All right. So here is some data. What will be the output voltage if our base resistance for our strain gauges is 120 ohms? Lambda equals 2, that's the gauge factor for our strain gauges. And this is our strain 10 to the minus 6. Remember, strain doesn't have a unit, right? Because it's change in displacement over displacement, or change in length over length. VS, our supply voltage for the bridge, and for the strain gauges is 15 volts. And in this case, we're going to connect it to an amplifier. We're going to have a feedback of 1 megohm. All right, so this is the configuration here. We have our 4 strain gauges configured in a Wheatstone bridge pattern. All right, so we'd say that 2 of these, R1 and R3, are in compressive strain. So they're in line with the load. And 2 of them, R2 and R4, are in tensile strain. And so those are perpendicular to the load. So when the load squishes this block, wouldn't squish it much, but applies a strain to it. These resistances R1 and R3 are going to decrease because they're compressive, and the tensile ones, R2 and R4, they're going to increase because they're in tensile strain. And what we really want is we want to measure the difference between V1 on this branch and V2. Now the way it's configured, R1, R3, compressive, compressive, tensile, tensile, as this one reduces, this one will be increasing. So basically, you're going to get a change in the voltage at this point. Whilst this one is increasing in its resistance, this strain gauge is going to be having a reduced resistance. So you're going to get, as the load applies, then what's going to happen is that you're going to get a falling voltage here and a rising voltage here. So the voltages at V1 and V2 are basically moving by equal magnitude in opposite directions. So you're kind of doubling the difference, if you like, right, between them. And that's one of the characteristics of how you configure a load cell. So we got a nice little amplification effect by doing that, but still the output voltage might be pretty small. So that's why we've incorporated a differential amplifier. And our gain, or our feedback resistance is RF 1 megohm. So what we want to know is, given these data, given the strain we've got 10 to the minus 6 with that particular load factor, what is our output going to be? What's our output at V out here after it's gone through the amplifier? Right. Now, a trick that we have to bear in mind with this problem is that we don't really have a clear input resistance. If we go back, you see here, our output voltage for this diff amp is the differential voltage times our feedback over our input. And the feedback and ground resistance are matched, and the two input resistances are matched as well. But in this case, what's our input resistance? What's our R1? Well, we know what our feedback is, and we've got our ground resistor there. But how do we define what R1 is? And that's a little trick with this particular problem. And what you have to look at is look at the voltage V1, or consider how you're looking back from here to the supply. And basically, where you've got these two resistors and the supply voltage across them, they're effectively in parallel, right? So the total drop in voltage across these two come through parallel resistors. And since they're parallel, then you're going to be applying that same rule, the potential difference rule to them. Basically, parallel resistors, the total resistance is going to be the R1 over R1 plus R4 plus R4 over R1 plus R4, right? So that's how you calculate the parallel resistance, and that's what you use. Now, R1 and R4 are going to be slightly different because one's increasing in resistance, the other's reducing. But since the gain, or let's say the strain, is very small, you can more or less average it for this purpose to get the input resistance. You could average it and say, well, we can take the resistances without taking that into account. Right? So the effective input resistance is going to be simply half of the base resistance of each of these, right? So that's going to be R out upon 2. Right? That's how we get our input resistance. These are acting in parallel. And the same will be true on this side for this branch. So both of these, if you imagine these kind of like reduce to 1 input resistor, it's reduced to 1 input resistor, and the value of each one is half of your R0, your base resistance. Right, so that's a trick we need to bear in mind. Once we've taken that into account, we can work through the problem. So R1 and R3 are compressive strain. So if R2, R1 and R3 are compressive strain. That means that we are seeing an increase in our resistance. Well, it should be a resistance, but a reduction. R1 and R3 are in compressive strain. So the resistance, I think these actually should be the other way around. It won't make a difference to the solution. Whereas if R1 and R3 are in compressive strain, then what we'd expect is that the resistance will go down, right? It'll go down. So actually, R1 and R3 should be our base resistance times 1 minus lambda epsilon, I believe. Because our resistance of R1 and R3, they're being compressive, that will be reducing as a strain is exerted on this load cell. And for R2 and R4, this should be a plus. It won't actually make a difference, right? Because you'll still get the relative difference between the two being amplified. It'll make a sign difference, that's your polarity difference. So taking that into account, basically you've got R1 and R3 are both going to be R0 times 1 minus lambda epsilon. R2 and R4 are both going to be R0, your base resistance, times 1 minus plus lambda epsilon. That's the change in resistance due to the compression of the strain gauge. You'll remember this from strain gauges, right? You can revise that for your in-course test, I presume. Okay. All right. Since epsilon is much less than 1, we can kind of like, for some purposes, neglect it and say R1 equals R3 equals R0. That's where I came to this issue of identifying what your input resistance is for this op-amp, for this differential amp. And that's why I said, okay, you have to combine these in both cases and take what's effectively the half the base resistance, since one branch of the bridge is a potential divider and the resistors are effectively in parallel. And since your strain is much less than 1, then we can say that the input resistance is going to be our base resistance divided by 2. Right? So having established that, we can now look at V1 and V2 separately. V1 is this point here, V2 is this point here. So for each of those, our V1 is going to be our source times our ratio of resistances. And R4 is the one that's going to be, R4 is tensile, so that's going to be a positive sign on the top. So it's going to be R0. You write it down. R4 equals R0 into 1 minus plus lambda epsilon. And we just said R1 and R3 equals R0 into 1 minus lambda epsilon. Right, so the resistance is reducing here. So when we substitute those into this potential divider law rule, okay, so multiplying out the bottom part, then you get R0 plus R0 times R0 lambda epsilon minus R0 lambda epsilon. So you end up with R0 over 1 plus lambda epsilon on the top over R0 times 2 on the bottom. So the R naughts cancel, and you just end up with Vs times 1 plus lambda epsilon over 2, which is what we have here, right? And for the other equation, which is on the other branch, it will just be opposite that. So this branch, now your compressive and tensile resistors are flipped. So you get the kind of equal and opposite equation for V2, for the voltage at this point right here. All right. Now, our output voltage, because we're dealing with a differential amp, we just learned our differential amp gain is the feedback resistance over the input resistance times the difference between your voltages. So now we have expression for our V1, expression for V2. All right, and when we substitute those in, when we substitute in the value for R in, remember we said we're combining those two resistors on each branch, using the parallel resistance rule, then it's R0 upon 2. So this becomes R0 upon 2. RF is as is. We substitute in V2 here, V1 here. These are negative, so they cancel out. You just end up with 2 RF upon R0 times your source voltage times your gauge factor times your strain. All right, so we have a nice little equation, but now we need to substitute in the values we had from the outset we were given at the start of the question. So this is the output from a diff amp applied to a strain gauge load cell. It looks like that. And we got there through derivation. So now we can apply our values. RF is 10 to the 6th, 1 meg ohm, right, as our feedback resistor. Our base resistance was what? 120 ohms. So you see very small resistance compared to the feedback sense resistor. Our source voltage, we said at the beginning of the question, was 15 volts. Lambda, the gauge factor, is 2, fairly typical. And then our strain was 10 to the minus 6. So substitute those in, work it all through. And you end up with 60 over 120 or 0.5 volts. So that's the output voltage from this setup. So that's a reasonable kind of output voltage that you can work with. It's not in the micro or millivolts ranges, which would be difficult. It's brought it up. So we've now applied our differential amp to a Wheatstone bridge, or in this case, a load cell setup, and got an output. Okay, so that's differential amp with an example. Now let's look at another one, AC amplifier. So the difference here, what's the big difference between this and what we've seen before? AC current. And what's the implication of AC current versus DC? Sorry? Yeah, it's good. It's a sinusoidal input, so you're not going to have a steady input, but you're going to have an input with a certain magnitude, right? And the magnitude of that AC signal is going to vary to define the RMS voltage, what's called the root mean square voltage. So with an AC signal or an AC voltage, we are not interested. Well, what we'd use would be the RMS, the root mean square voltage, to get the magnitude. But because it's varying, what you're doing is your whole system, your whole circuit will be continually in flux, right? So as voltage goes up, you get an output rise in voltage and decrease in voltage. And what you need to build into this circuit is some way of of storing and discharging charge, which is why you have capacitors, right? So these capacitors effectively create some lag in the system, because as the voltage increases or as your current goes positive, it charges these capacitors, and then when it starts to be, when the voltage starts to drop off and goes negative, the capacitors are fully charged and then they start to discharge. So you're introducing a lag. And that's a realistic element in an op-amp or in an amplifier circuit. But what it does introduce this kind of phase lag. So your input will be on one phase, the output will be on the same frequency, but there'll be a phase lag. So it'll be peaking at some angle or some time after the input peaks. And when it drops down to its minimum value, this will be lagging behind. So you get this phase lag effect created by these capacitors in the circuit. But what that also does is, where we talk about resistances most of the time, and we've got to interchange resistance and impedance, this is now a true impedance. Because the true impedance is made up of three elements: resistance, which we're familiar with, capacitance, and inductance. We don't have any inductance in this one, but we do have capacitance. So now we have to use a different sort of expression for impedance. I'm not sure whether you've covered complex impedance before. Have you covered that? Electrical tech? Right, so you're familiar with this then. Okay, that helps me. What type of op-amp is this? Or what type of amplifier circuit? The positive pole is connected to the ground line, right? Or to the negative. So this is an AC inverting amp. So an AC input is connected through an inverting amp with input resistance and capacitance, Rn and Cn, feedback resistance and capacitance, the feedback here, Rf and Cf. All right, so what's the equation? Well, the DC equation is this: V out is the gain, negative gain times your input. It basically holds for the AC, but now we have to convert our Rn and Rf into their impedance equivalents. So it's taking the capacitance into account. And our impedance for the input is going to be the product of the sum of our input resistance and our input capacitance. Now we've introduced this S, which is the Laplace operator. You covered Laplace yet? No? Well, you cover Laplace in maths, hopefully before the end of the semester, because you'll need it. That's the first thing we do within controls. Right? So this Laplace operator, basically this represents a differential equation. And Laplace transforms are a way of solving differential equations, of simplifying them to solve them. So this is basically an algebraic representation of d by dt. So that means that you have you have dynamics in this capacitance. The resistor doesn't have any dynamics, but the capacitor has dynamics associated with it, a differential term. Or in fact, in this case, is actually an integral term, because it's adding up charge. It stores charge, then it releases it. That's an integral function. It adds up the charge over time and stores it. So the 1 upon S you have in this function is basically indicating an integral effect. So you can multiply that, you can multiply that out, but we also have an impedance equivalent for the feedback side. Now this one is in parallel. So you have to use the parallel voltage rule for that. So the total impedance, sorry, not the voltage rule, the parallel resistance or impedance rule. So the overall expression is Rf over Rf Cf S plus 1. As I said, S is this thing called the Laplace operator, which we'll learn about shortly, not in this course, in your maths. And so what we end up with here, when we substitute this ZF and Zin for RF and Rn, and we multiply out, we end up getting a relationship between our output on RMS, this bar on top of the V, That would indicate that's the RMS output over the RMS input. The ratio of those would be minus RF upon Rin into 1 upon CFS, RC S plus 1 times RNCN over S over RNCN S plus 1. Again, you get that by substituting and working through. I'm not going to do that right now. You could do that in your own time. Just drop those values in. You should get that. Now, the complexity with an AC amplifier is it doesn't amplify consistently across all frequencies. So if you have a higher frequency from the sensor, say, then you might find that the amplification changes. Or if you have a low frequency from the sensor, the amplification changes, or the gain of the amplifier circuit. At high frequencies and low frequencies, the amplification drops off in a non-linear fashion. But in the mid-band, we should get a nice relationship RF upon Rin. So this is a diagram showing the relationship between frequency here, because remember you've got an alternating current, so that alternating current is a sinusoidal form. That sinusoid has a frequency. If you go down to low frequencies, you see there's a drop-off in the gain. This is your gain, your output over your input. Through this mid-band, between F1 and F2, our threshold frequencies, we have a fairly nice, stable, consistent output of RF upon Rin. Once you go above it, it drops off. You notice that here we have another dashed line, just slightly below the kind of unity relationship or the standard relationship. This actually represents your bandwidth, right? And you heard bandwidth is a familiar term. This is what it means. It means the frequencies between which you get less than 3 decibels drop off in your amplification. All right, so the bandwidth of this particular device is F2 minus F1. That's a bandwidth. That's the range of frequencies over which its characteristics are fairly consistent. And you can calculate the bandwidth using these equations. We don't need to go into that. All right, so that's an AC amplifier. So the last part of this lecture, we're going to look at instrumentation amplifiers. Now, instrumentation amplifiers are basically high-performance devices. So these are the kind of amplifiers that would be sold on the market specifically for the purposes of instrumentation. The other ones we looked at are basically configurable op-amps. You know, you take the basic parts, put them together. But this instrumentation amplifier is a high-performance differential amplifier. And what it does is it kind of stacks up a number of if you like, subsidiary amplifier circuits into one. And what it gives you is, it should give you a high quality output, basically. And it gives you things like really ensuring you get that high impedance input, the low impedance output. And what an instrumentation amplifier also does is it allows you to change your overall gain by just changing one resistor. Why is that important? If we compare it to a differential amp, so an instrumentation amp will more or less do what a differential amp does. But looking at our diff amp here, you notice what do you need to change if you want to change the gain of this amp? You have to change R2 or your feedback resistor and your ground resistor. You have to change both of those, and you have to change both of these, right? Or you wouldn't necessarily have to change both. You certainly have to change at least 2 resistors here to get an overall change in gain. That could be problematic because one is tricky, you know, you actually have to change them out. But also every resistor is slightly different. So even though they're nominally identical or have the identical characteristics, have the identical resistance, in reality you do have manufacturing variability in all electronics. So they're going to be slightly different, and that's going to affect then the overall, you know, that'll be a source of uncertainty in the amplification of your diff amp. right? So an instrumentation amp allows you to change your gain K by just changing one resistor. And K, in this case, your gain is precisely known and can be varied over a large range. So an instrumentation amp should have, like I said, a gain K could be set by a single external resistance, a high input impedance, or it should have a high CMRR. What's CMMR stand for? Common mode rejection ratio. And it means what? How much voltage that's applied to both poles of an amp is actually transmitted, right? So ideally, you don't want to have any voltage applied to both poles amplified at all. You only want the differential, or the difference between those two poles amplified. And the common mode rejection ratio tells you how much actually is. Has a low input offset voltage. That's just one of the and low temperature characteristics. These ones indicate that they're sources of uncertainty or error in your amp. You don't want, you ideally have zero in both of those cases. All right, as I said, a basic diff amp is highly susceptible to mismatch in those resistance values. If you get a difference between your ground resistor and your feedback resistor, it's going to create errors in your circuit. So this is a schematic of an instrumentation amp. So you have like basically 1, 2, 3 diff amps. And what you have here is a negative pole of these two that connects together through one resistor. This is the resistor you can change to change the overall gain of the system. Okay. Again, this if you're into that kind of thing, a nice problem to work through to get the overall equations or to derive them. You notice on the output resistor here, on the output amplifier, R2, 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 right? So this one, what's the overall gain of this part here? This is a unity output, right? Unity gain. Because you have the same input resistance on this differential amp as feedback resistance and ground resistance. So that means this part here, it doesn't do any amplifying. All it does is it provides, again, like the voltage follower, provides the characteristics you want. So it allows you to have a high or a low output impedance. Your two input voltages are here and here. And basically the relationship or the gain is given by this value R1 divided by your RG in each case. So the overall differential gain of A is A, which is 1 plus 2 R1 upon RG. And your common mode is basically about 1, the common mode gain. So that means that it has a good common mode rejection ratio. And as I said, this little amplifier circuit here, this is a unity gain diff amp. Doesn't add any actual further gain. This is an extract from like a data sheet for an instrumentation amp. This is AD620, and basically it'll come as a microchip. So you just put this into your circuit when you're building a circuit for your instrumentation system. And it will have pins down the side. These little, the little silver legs that come out of the microchips. That's what these represent. And you connect them up in a particular way. It tells you on this data sheet. This is just a small extract of the data sheet. But it tells you what all these pin out, or what your pin out is for this particular instrumentation amp. To start with, you have plus and minus VS. What's that for? That's the power. That's to power the amp. The supply voltage. So it requires a bit of power. What else do we have here? Well, we have plus and minus input, right? And then we have an output. So 2 and 3 are your inputs. That would be equivalent to V1 and V2 on this diagram. And we also have an output here. But here you see we've got 1 and 8, both labeled RG. So what does this do? What's that for then? Note that on this diagram, RG is identified here, right? I said that you can change out your RG, your gain resistance, to give you different overall gains for this particular amplifier. So what it allows us to do is basically externally connect some resistor. And whatever you put here, that will determine what the overall gain of this op-amp is. So when you connect up your inputs here, the output will be the difference between 2 and 3, the voltages on 2 and 3, times your gain. And what you can actually do with this op-amp is, with one external resistor, you can change the gain from a gain of unity to up to 10,000, right? Depending on the resistance of this gain resistor that you select and you plug in. It can handle a wide supply range, that's your supply voltage. What else? And these are some specs about how it behaves. So this is your input offset voltage, 50 microvolts max. So if you want to calculate your errors, what we call the error budget, or the uncertainty of your output, then these data will be very important for you, because this will tell you whether the thing so you've got the same inputs on 2 and 3, will it give any outputs? Well, yes, it will. It will give a maximum 50 microvolts output, even though it should be 0. So that's the source of uncertainty. It will also change that output by 0.6 microvolts per degree C. So as temperature changes, it's actually going to generate a little output voltage that's a false output voltage. So this is derived experimentally, and it'll help you when you're implementing a measurement circuit or instrumentation system to know how confident can I be in the output value that I'm getting from my amplifier. Let's just talk a bit more about common mode rejection ratio. I've been referring to it because something that I was wanting to explain. Oh, there's a video here. I'll play you this. It's a video on an instrumentation amp. Try and get sound. It doesn't seem to want to.
The term instrument is properly used to describe a category of true differential input amplifiers that emphasize high common mode rejection and accuracy. More commonly, the term instrumentation amplifier is not used, and instead the wide category of instrumentation amplifiers, or IAs, is broken up into 3 more specific categories of 2 or 3 stage instrumentation amplifiers, difference amplifiers, and current shunt monitors.
So 2 or 3
PI has an active portfolio in each of these 3 areas, but it's the 2 or 3 stage instrumentation amplifiers that are the focus for today. Different high CMRR and high gain in just
I think that's good enough there. Just to give you an idea, that's Texas Instruments product offering of instrumentation amps. And you saw the diagram looking like the one that I showed. It introduced the fact that there's another type, which is a two-stage instrumentation amp. So there are different configurations. The one we looked at is this three-stage one. Okay. So let's look quickly at common mode rejection ratio. Okay, so an ideal amp, differential amp or instrumentation amp, it provides an output voltage with respect to ground as the gain times the difference of these two voltages. So it should just give you V2 minus V1 times whatever gain you've applied. But the output voltage doesn't just depend on, or should only depend on the difference, right? So, but did you think about what happens if this is 0.1 and this is 0.08, right? Versus what happens if this is 100 and this is 80? Or, yeah, that's right. Same. Or no, it'd be 100 and 99.998. Right? So it's the same difference, the same delta, but the level is very different. Is the amplification effect going to be the same? So there's a slightly different way to look at this issue of common mode. Or if your amplification's gain is 10, V1 is 0.3, V2 is 0.2, then your output voltage is going to be 1 volt or minus 1. Likewise, if you even just got a little more, which is 7 volts to 7.7 volts, you still have the same output voltage nominally. But real amps only approach this ideal, because the ideal is that the delta is what you get as your output. In reality, you get the delta output from this part, which is the same as this, but then you also get another bit, which is called your common mode output, right? And that depends on your common mode gain. And ideally, your common mode gain should be 1. But in reality, it might not be. So our common mode input voltage is the average of our two voltages. So that'll be very different for these two examples. The average here is 0.25. The average here is 7.65, right? Very different. So for an ideal output from a diff amp, the common mode output, like I said, will be 0. But in fact, common mode rejection ratio is defined as the ratio between the differential gain to the actual common mode gain. So this is our differential. So in the example I just gave, this is 10 divided by what? What's our common mode gain? So if we have a common mode gain of 1, it'd be 10 to 1. Our common mode rejection ratio would be 10. Right? Normally it's expressed as a decibel. So normally we take that ratio and we make it into a decibel. To make a ratio into a decibel, you take log 10 of the ratio and you multiply it by 20. And that's the decibel scale. And we'll be using that a lot in controls as well when we get into control. So one of the nice things about a decibel scale is you can take something that's inherently has a nonlinear relationship or a logarithmic, and it linearizes it. Right, so that's why we tend to use decibels. So this will give us our common mode rejection ratio. If you recall, last time I put up a data table at the beginning of the lecture with a set of data about an ideal op-amp versus an actual op-amp. The ideal op-amp common mode rejection ratio was infinite. Yeah, so that means your common mode rejection ratio would be infinite decibels as well. The reality was, the other column had about 120 decibels, right? So that would have come from this calculation here. What's the amplification or the gain of that amplifier versus the common mode gain from the same amplifier? And typically our common mode rejection ratio is in this range of decibels, 60 to 110. One of the causes of common mode rejection ratio not being ideal is that we have these mismatched resistors. So where you're supposed to have resistors of the same value, like in a differential amp where your feedback resistor and your ground resistor are supposed to be the same. If they are not the same, if they have some uncertainty like manufacturing tolerances, that creates a certain less than ideal common mode rejection ratio. So this is a relationship between your resistance or your resistor tolerances and the common mode gain that's generated by those. Because basically what happens is if you have mismatched resistors where you have a common mode, it's going to say you have a V1 and a V2. If your resistors are mismatched, there'll be a difference in the amplification effect of those two voltages. So instead of just being V1 minus V2, you're going to get the value of V1 and V2 factoring into it because of this mismatch in our resistors. Right? So that's where this common mode rejection ratio comes from. The more precise your tolerance on your resistors, then the higher this is, and the more common mode you reject. So that's it basically for amplifiers. There's a couple of example problems here, which we can run through, or I think one, and then I'll give you some tutorial questions at the end of this. So on my learning in the notes already, so you can check those out. All right, so let's look at this example. A sensor output ranges from 20 to 250 millivolts. As a variable over its range, we want signal conditioning, so this becomes 0 to 5 volts. Very realistic problem, this one. The output must be accurate, and the circuit must have very high input impedance. Why? To keep the heat dissipation in the sensor low. Keep the current on the sensor side low. Assume a supply voltage of 12 volts. So what we're going to start with is start by defining a relationship between our input and our output, right? So then, our input, let's call it V min, is 20 millivolts, and that has to go to 0 volts, right? And our V max input is 250 millivolts. That has to go to 5 volts. Now, assuming there's a linear relationship, basically what you've just done is define 2 points on the straight line. So, if the horizontal axis, the ordinance is V in, and the vertical, or this could be out, then we've defined the point here, and this point is, V1 should be right here, right, on the 0 volts line. This goes 0 to 5, this goes 20 times 10 to the minus 3, and both of these are volts. And it goes up to 250 times 10 to the minus 3, gives you 5 volts. So now we just have to draw a nice straight line. Nice straight line between these points. All we need to do is define what's our gradient M, right, and what's our intercept C. Can you do that? This is 250 times 10 to the minus 3, 5. And this is 20 times 10 to the minus 3, 0. So what's the relationship here? We want to get the relationship as V out equals MV in plus V naught. So V naught is your C, M is your gradient. And we've got this relationship here. Now M, or your slope, that's the gain of your amplifier. And the V naught is the offset voltage that you need to apply. Remember from the earlier examples, you had the summing amps, where we had the kind of constant voltage and then the variable voltage. So we have to apply a constant voltage to this one. All right, given time, I have to define the this for you. We have two conditions: 0 volts output equals M times 0.02, 20 milliamps to millivolts, sorry, plus V naught. You don't know what V naught is. Next condition, 5, gives us 250 millivolts plus V naught. Well, two equations, two unknowns, so we can solve those. By solving it, we get our output voltage is 21.7 times our input voltage minus 0.343. So when we factorize that, we get 21.7 times V in minus 0.02. So we have V in on one branch, if you like, V out, and a constant of minus 0.02 on the other one. So you have to have those two and then multiply it by an overall gain of 21.7. So we have to design a little circuit for that. And this looks like a differential amp then, with a gain of 21.7 and a fixed input of minus 0.02 on the inverting side, negative value. So the question said we have a supply voltage of 12 volts. So we have to take that 12 volts down to 0.02, right? Because we have to apply a constant 0.02. So something inside this design of this circuit has to go from 12 down to 0.02. And well, this is what it would look like, right? So let's jump into the solution a bit here, but at this end here, this is where we get our amplification, because we've got our 217 kilo ohms divided by 10 kilo ohms, right? That's our RF over our over our in. So down below here, we get our input voltage. It goes through a voltage follower. Why does it have a voltage follower? What does a voltage follower do? It kind of creates a buffer, creates a separation. In this case, it creates a very high input impedance. Because we said when we looked at the voltage follower, the input impedance of this amplifier becomes the input impedance of the op-amp, which is maybe 30 mega ohms or something. So this gives us our nice high input impedance, which was specified in our question. But the voltage output is the same as the voltage input because it's a gain of 1. There's no gain on that. So now we go through our inputs here. We've got our ratio, so we're going to have our V out equals V in times 21.7, our gain. And so on this branch now, we need to get our minus 0.02. How do we do that? Well, we have to take our 12 volts down to 0.02. And you can do that basically using a potential divider. Ignore this for now. Basically, you can go 12 volts down by having a very large resistor and a very small one as your two elements of your potential divider. You could get 12 volts to 0.02 volts, right? Now, the only problem with that is because of the small voltages involved, it gives a slightly unstable or volatile reference voltage here, right? Or constant voltage. So that's why this solution has these elements. This is a diode which stabilizes the voltage input, right, and gives us a steady voltage at this point. So then we can be pretty confident that the 0.02 volts on this branch here is stable. And so what this voltage follower here does here, this flips it because this is connected to ground. The positive pole is actually connected through to ground. That means this is an inverting amp. So our plus 0.02 gets flipped to minus 0.02. That's how we get it here. And now we get our overall output voltage according to the relationship we wanted, which is this here. All right, so that's how you kind of create an amplifier circuit to give you a particular relationship. At the end here, we've got a couple of tutorial questions. This is a past paper question, which you might be interested in taking a look at. And this is a Wheatstone bridge related one, similar to the one we looked at with our load cell in class. Okay, so that's it for this signal amplifiers part B. And don't forget Friday, everybody, and be here promptly so we can start with our friends from Germany.